Greetings, my name is Aiman Abdullah Ahmed Omar. I am from Group 3 and I am going to present my project, which is three-phase Y generator. So let's start. What is a three-phase generator? A three-phase generator generates power in three phases 120 degrees apart. Each phase is measured from phase to phase, like V phase 1, V phase 2, V phase 3. All three phases are joined to a common point known as neutral. A good example of these phases at 120 degrees apart is to look at the Mercedes badge. It has 120 degrees with the common point at the center. Measuring the power from the center point to any of the outer points will give you the single phase power value. So for example, like VPS1 to center point neutral is 230 volts. From outer tip to outer tip on any two of the three outer points, you will get 400 volts. It's cheaper to generate three-phase power than single phase power. This is the figures for the positive sequence and the negative sequence of the phases. On the left hand side is the positive sequence, which APC. So from each phase to phase is 120 degrees apart. For the positive sequence, we'll move clockwise, and on the right hand side for the negative sequence, which is ACP, we're gonna move anti-clockwise. So from VN to VPN, it's 120 degrees different, positive or negative. This is the circuit that the project based on. It's a Y to Y connection generator, three-phase. The objectives of this project is to evaluate the parameters of the electrical system in the context of transmission and load impedance, current, voltage, and acceptable voltage drop based on PS7671 or any Malaysia's 30 standards. To evaluate and analyze the active power absorbed by the loads, and to justify the normal operating condition of the electrical system and validate the study with the simulation. The methodology: this project conducted using two water meter method and the conventional measuring method to measure the power absorbed by the loads, also using computer software like PSIM for the simulation part to validate the report result with the simulation. We construct a three-phase Y to Y circuit with the V line that been given and the resistance, also the reactance that also been given beforehand. We will find the currents, voltage drop, the active power absorbed by the loads, and the transmission loss for the simulation. We will construct the Y to Y circuit to verify our calculation result and justify it. So the impedance, voltage regulation, efficiency, and similar calculation for three-phase transformers are done on a per phase basis using exactly the same technique already developed for single phase transformers. So let's see the calculation, but first I will show the flow chart of the project. First, to observe what the objective of the report, then read more about PS7671, then construct the circuit using PSIM for simulation. After that, record the data and the result of the simulation. After that, do the calculation part to find the parameters. Then validate the calculation with simulation result, and finally discussion and conclusion. For the V line given in the question, which is 132 kilovolt, and the load is 81 plus 9J ohm. For the transmission resistance is 54 ohm. And because of the phase is positive, sequence of VAB equals to 130K, angle 0, so this is the reference, and the VBC and PCA will be the same on the magnitude, but the angle will change, which is 0, 100, minus 120, 120. To find the phase voltage, first V line leads the V phase by 30 degrees. So because it's three phase Y to Y, so the V phase equals to V line over square root of 3 degree angle 30, so 132K for volt or over square root of 3 angle 30, it will equal 76.21 K. So for the VAN, Vn equals to 76.21 K, my angle minus 30 volt. So for the VAN, VBN, VCN, it will be the same in magnitude, just the angle change. For the VAN minus 30 angle, and for VBN the angle will be minus 150, and for VCN the angle will be 90. To find the line current, which IAA, it's V phase A VAN, VAN over the Z load and the resistance of the transmission. So it will be 76.21 K, angle minus 30 over 81.49, angle 6.34 plus 54. So it will equal to 563.30 ampere, angle minus 33.81. And for the APPs it will equal to VPN over the loads, so it will equal 563.30, angle minus 153.81. and for the ICC it will equal to PCN over the load, so it will equal to 563.30, angle 86.18. and because I load equals to I phase, so IAA equals to IN, IPP equals to IPN, ICC equal to ICN. To find V phase load equals to V load over square root of 3, so 132 kilo over square root of 3 will equals to 76.21 kilovolt. To find the active power absorbed by the loads by using two wattmeter method, so the formula will be W1 equals to V load multiplied by I load cosine Q plus 30. Q, it's the angle of the load. So 132K multiplied by 563.30 cosine 6.34 plus 30, it will equals 894.53 kilowatt. And for W2 it's the same, we just gonna change it from Q plus 30 to Q minus 30. So after the calculation it will equal to 68,105.49 kilowatt. So the total power using the two wattmeter method will equal to P total equals to P1 plus P2, so it will equals to 128.02 kilowatt. And to find the power using other formula or other measuring method, so P load will equals to 3 multiplied by V phase load multiplied by I phase load cosine theta, so it will be 3 multiplied by 76.21 K multiplied by 563.30 cosine 6.34, so it will equal to 999.62 kilowatt. So it's the same values as by using two wattmeter method and the conventional method. For the power factor, the PS7671 say the consumer need required to maintain their load power factor to a minimum of 0.90 for a voltage level 132 kilovolt and above. For me, I did the calculation for the power factor, so I get 0.99 lagging. And for the transmission line loss, P loss equals to I square multiplied by R, so 563.30 square multiplied by 554, so it will equal to 17,134.57 kilowatt. For the voltage drop percentage equals to V supply minus V load over V supplies multiplied by 100%, so 132K minus 76.21K over 132K multiplied by 100, so it will be 42%. Based on the PS7671 standards, the voltage drop doesn't exceed a percentage of 5%. In my case, the voltage drop exceeded 5%, which is 42, so this is not the acceptable voltage drop percentage according to PS7671, so it is not in a normal steady state operating condition. For the power absorbed by the load, there is two ways to get the 2 watt-meter method and the B load formula, and we did get identical values for the power absorbed by the load. For the power factor, according to the electricity supply application handbook version 3.1 by TMP, it states that if the voltage less than 132 kilovolt, the power factor needs to be minimum of 0.85, and for 132 kilovolt and above, it needs to be a minimum of 0.90. In my case, my voltage is 132, so the power factor needs to be a minimum of 90, and after the calculation I get 0.99, so it's suitable. In conclusion, the three-phase Y to Y transformer is a three single-phase transformer. The Y connection joins together one end of each of the coils and applies the individual phases to the open ends. It has the same values for generator loads, but it's different from the angle for each phase, different by 120 angles between each phase. The phase current will equal to the line current because it's an Y connection, and the impedance are in the same value, so the system is balanced. And for the voltage drop percentage, in my case it's 42, so it's not as the standards given by the PS7671. So when voltage drop exceed, after research I see that when voltage drop exceed the values, the value of 500%, we need to use larger cables wires, most used to correct the condition, which means the system is not in a normal operating condition. And for the simulation, this is the circuit that we construct using PSIM, and this is the values we get for the current. We get for the I line for each phase of the load, we get 563.30 ampere, which is the same as our calculation and same with the simulation. And for the V phase, we get 76.21 kilovolt using our calculation, and when we did the simulation we get the same values. And